Vapor pressure is another physical property that has everything to do with intermolecular forces in a liquid that we're going to talk about next. So vapor pressure is the pressure of the vapor of a substance when the liquid and the vapor phases, so vapor, gas, when the liquid and the gas phase are in what we call dynamic equilibrium. So when we think about the word dynamic, we need to be thinking about moving. Another way I like to think about dynamic is if you ever play a sport, you do dynamic stretching, and those are stretches when you're moving. Static stretching are stretches when you're standing still. And so things in nature we know are never stagnant. Things in nature are always dynamic. And when things are in dynamic equilibrium, it means that there's equal parts of liquid and vapor, but they're always moving. So it's no net change, and we'll get to that idea in just a second. So if a liquid is in a closed container, some of the molecules will have enough kinetic energy to escape intermolecular forces and form the vapor phase. So essentially they're going to be able to evaporate. But if we have an open container, we're never actually going to reach dynamic equilibrium. So we have to have a closed container so that we can reach dynamic equilibrium where the molecules are entering the gas phase and the liquid phase at the same rate. So you don't have a net change. And so dynamic equilibrium must happen in a closed container. So how we measure vapor pressure, and when we talk about vapor pressure, we're going to be talking about intermolecular forces, and we're going to be talking about how much pressure those molecules have when they're in the gas phase. And we're going to use a manometer example to help us figure that out. So substances reach, again, dynamic equilibrium when there's no net change in particles in the gas phase. Again, even though the gas and the liquid particles are in constant flux, there's no net change. So equilibrium and no net change are two words that definitely go together. So the vapor pressure, which is the molecules that are in the gas phase, so if I've got water in a manometer, for example, I would have a certain amount of those molecules, water molecules, in the gas phase. And the vapor pressure is just the pressure that those gas water molecules are putting on that container. When I increase the temperature, I would increase the number of molecules being able to reach the vapor phase. So essentially, if I were to boil water, I'm going to increase the number of molecules there because I'm increasing the energy, and I'm increasing the molecule's ability to escape the intermolecular forces and actually reach the gas phase. And so if I increase the temperature, I'm going to increase the vapor pressure. And so if I've got molecules that have strong intermolecular forces, it might take me a little bit longer to boil that water, right? Because it's got a high boiling point. So I might not be able to increase the vapor pressure of a molecule with high intermolecular forces. Liquids with high vapor pressures, however, are what we call volatile. Anything that has a high vapor pressure is something that we're going to be able to smell very, very easily. So volatile liquids are simply liquids that evaporate easily. These guys have very, very low intermolecular forces. They have weak attractive forces between molecules. And so if I've got a liquid that's very volatile, that means that it's going to evaporate easily, which means that it can become a gas molecule very easily, which means it would have a high vapor pressure. So this is where people generally get confused with vapor pressure and boiling point and melting point. So if I've got something that's evaporating easily and it's got weak intermolecular forces, that means that it would not take a lot of energy to get those molecules to boil. And so it would have a low boiling point and a low melting point. However, it would have a high vapor pressure. If I've got molecules that have high intermolecular forces, like water, for example, it takes a lot of energy to boil water. If you remember, so we're going to answer the would water be volatile question. So water would not be volatile because it has a lot of hydrogen bonding. It's got a lot of attraction. And you actually calculated that attraction in the first semester, and when we did our EOC practical, where we measured that the specific heat of water is 4.184 joules per gram degree Celsius. So we know that it takes 4.184 joules to raise 1 gram of water 1 degree Celsius. That's a lot of energy. So that means that water molecules do not enter the gas phase very easily. So the vapor pressure of water would be very low. So if it's got a high boiling point, it means that it's got a low vapor pressure. On the other hand, CH4, would that be volatile? So this is a molecule that has London dispersion forces acting on it only because it's a nonpolar molecule. So it has no attraction or very little attraction to other molecules within the liquid form. And so those molecules would be able to evaporate very, very easily because, again, they have weak attractive forces. So because they evaporate easily, the boiling point would be very low. But that also means that the vapor pressure would be high. And so this is going to take some time to make sure that we understand this, but if you've got a high intermolecular force, you've got a high boiling point. And so those molecules don't enter the gas phase very easily, and the vapor pressure would be low. And vice versa, if you have low intermolecular forces, it's going to evaporate easily, which means you would have low boiling points and high vapor pressures. So here's an example of something in dynamic equilibrium. And we've got examples of these on the front that we'll talk about on block day, where we've had rubbing alcohol and water sitting in a flask for over the weekend, and those molecules have reached dynamic equilibrium. There's an equal amount of liquids and gases in there. We've had it closed for quite a few days, so we know that those molecules are in dynamic equilibrium. And what we've done is we've put a pressure sensor with that, so now we can measure vapor pressure. So if this is water right here, we would assume that there would not be as many gas molecules because it's got high intermolecular forces. And so those gas molecules don't overcome those forces as readily as, say, maybe a CH4 molecule that's got low intermolecular forces. So the best way to measure vapor pressure is thinking about a manometer. So if I had water in here, and I've got my manometer here and I'm reading the vapor pressure and I can read the height, water molecules would not be in the gas phase as readily. And so if I have water right here, okay, and I've got the gas molecules, it would be maybe forcing that down just a little bit. If I had rubbing alcohol or gasoline or acetone, which is nail polish remover, again, anything that we can smell easily that's still in the liquid phase, I might have much more molecules in the gas phase, which would force this out greater. And so my vapor pressure of molecules that I can smell really easily, that are what we call volatile again, would have a high vapor pressure. So it might start here and end here. We might push the liquid mercury all the way out to there, showing that it's got a high vapor pressure. But a high vapor pressure would equal, so I'm going to say high vapor pressure equals low boiling point. And that's really important because it's got low IMFs. And we need to make sure that we can keep those distinctions together. Okay, so a high vapor pressure means it's a low boiling point and low intermolecular forces. Here's another example of something where we're looking at vapor pressures. So I've got water vapor pressure, I've got an alcohol vapor pressure, and then I've got another one here that's got really high vapor pressure. So this would have low intermolecular forces compared to water, which would have high intermolecular forces. And then we can say, okay, so if it's got high intermolecular forces, it's also going to have a high boiling point and high melting point. I'm just going to put a slash MP there so that we know that that's high boiling point and high melting point. If it's got low intermolecular forces, we know that it's got a high vapor pressure, so high vapor pressure, and low boiling point and melting point. We can come back over to water now and say that it's also got, if it's got a high boiling point and melting point, it's got a low vapor pressure, because not many of those molecules, as we can see right here, are in the gas phase. Where we can see here, these molecules have a much higher vapor pressure, so that means that we know it's got low intermolecular forces, thus low boiling points and low melting points.